Hello and welcome to Eng Phys 2P04 Lecture 23, Simple Piezoelectrics. So in piezoelectric materials, there's a crystal asymmetry, so there's an asymmetric crystal structure, and there's also a charge asymmetry. You might have some atoms that are more negatively charged than other atoms, perhaps because they are more electronegative, so they hold on to the charge a little bit more than the other atoms do. Okay, so in these materials, when you deform them, then you cause an electric field to show up. So this moves charge around in such a way that an electric field shows up, which means that you can deform them to get electric fields, or you can apply electric fields to cause deformations. In short, the electrical and stress fields are now coupled to the strain. So some simple piezoelectric calculations would just say that piezoelectricity is analogous to thermal strain. You've got the total strain now is not just the mechanical strain, but it's also the thermal strain like we had last lecture, and the piezoelectric strain, where the piezoelectric strain is given by d piezo times E here is the electric field, where as in this part of the equation, it's the Young's modulus. So whenever we've got them both in the same equation, we're going to have to be careful to call one of them something different. So maybe E field or EY for Young's modulus if we're typing it into a program. Okay, so the difference is that the electric field can cause different strains in different directions. So maybe the electric field in the Z direction, like in PZT, this, for example, here's the numbers for PZT. Electric field in the Z direction causes a negative strain in X and Y, and a different positive strain in the Z direction. If you apply an electric field in the negative Z direction rather than the positive Z direction, then it would cause the opposite strains there. These strains in these directions would consequently cause electric fields in the Z direction as well. We're not going to look at the production of electric fields from strains until we look at until we get into the next lecture, though. So for now, let's just assume that you've been given the electric field in all of the calculations, or at least given material that lets you find the electric field, like the voltage and the displacement it's applied across, and you're going to be using that and an equation like this to figure out what the strains are. Okay, so first example is a PZT linear actuator. PZT is a piezoelectric material that has this setup, so it couples Z electric fields into strains in all the different directions. It doesn't couple electric fields in X and Y into these strains, though. So we're only concerned with Z-directed electric fields for PZT. Two gold electrodes are placed on opposite sides of a thin PZT slab, shown below. So this is 1 millimeter thick, and let's say 5 centimeters long, and 1 centimeter wide, the width being into the page in the Y direction. And we're told that this is the positive X direction. Z direction is up. And so by using the right-hand rule, X cross Y is supposed to be Z for a right-handed coordinate system. Y is into the page rather than out of the page, if that matters. Now, hooking up the gold electrodes to a DC power supply, you place a potential difference of 100 volts on the top surface relative to the bottom surface, which makes the electric field point down. Electric field, you may remember, is equal to negative the gradient of the electric potential. So it's negative 100 volts per millimeter in the Z direction. Assuming that the bar is free to move, meaning that there's no stress applied on any of the faces, find the strains in all three directions due to this field, and find the new dimensions of the slab. Okay, well, all we have to do is substitute the field we found into this equation to get the strains. Ta-da! And to find the new dimensions, we just take the new length is the original length times 1 plus the strain, as before. Not so bad. Okay, well, let's have a look at these numbers here. 100 volts over a millimeter sounds like a fairly decent voltage, yeah? The DC voltage supplies that you'd probably be dealing with in an undergraduate lab don't even go up this high, right? So you are not physically able to apply a voltage higher than this in the laboratory setting yet. Although other people can do that, but you guys can't. Maybe if you're really lucky, then you'll have access to higher voltage power supply. But a couple thousand volts is a pretty decent voltage to find in a power supply. So look at the displacements that you get from this. The deformations that result from this this voltage applied are really small. Like, we have to add in all these decimal points just to get these numbers to show up. So the new length of this bar in X is not 5 centimeters anymore. It's 5 centimeters plus almost 1 micron. You'd be very hard pressed to notice this deformation right away. So we'll look at ways to amplify this deformation in when we look at flexure. In the bending section, there's certain tricks that you can use to get much larger deformations. For now, the one thing that you could immediately do to make the deformation bigger is you could make this slab a lot thinner. So if instead of 1 millimeter, you were to have a 1 micron slab, then we'd have a deformation that's almost a millimeter long. That's still not that impressive if it has to be 5 centimeters to do that. And one thing to worry about there is that you might be approaching the, or passing even, the breakdown field of PZT. So that's something to be concerned with when you're applying these really high voltages. One more example for today. Modify your FlexPDE to account for PZT5A with a known electric field in the Z direction EZ, given that PZT5A has a stiffness matrix of this and a compliance matrix of this. So it's going to be very similar to the change for thermal expansion, except that now we have to add in a different strain in all 3 dimensions based on these calculations in terms of EZ. So all we'll do is say that EX mechanical is equal to EX minus D piezo ZX times E field Z, and similarly for Y and Z, same as it was for the thermal strain. Great.